Okay, so next up we have refinement through restraint, bringing down the cost of verification. Liam O'Connor will be presenting, and this is joint work with Zilin Chen, Christine Rizkala, Sydney Amani, Japheth Lim, Toby Murray, Yutaka Nagashima, Thomas Sewell, Gerwin Klein. Clearly we need to bring down the cost of verification.
All right, thanks, Kathleen. So today I'm going to talk to you about some work that I did with the Trustworthy Systems team at NICTA, and you've already heard some of their names. Sorry, it should be called Data 61 now. And so this Trustworthy Systems team was founded as the union of two very different but equally important groups. The first one is the operating system engineers, who were very interested in low-level systems programming, and they really like to hack on kernels and stuff like that. And then we have the formal methods people, who probably haven't written an operating system before, but they both have a very common vision, and that is they want a truly trustworthy computing platform. So what that means is they want something that is backed by formal proof. So it'll be suitable for use in aeronautics or medical applications or anything where you'd be happy to entrust your life to a piece of software. So, I don't know, you might have heard about their first major triumph together, and this was the SEL4 microkernel. It's a general purpose microkernel in the L4 tradition. It's got the best performance of any L4 microkernel in terms of IPC. It's about 7,500 lines of C code that has been formally verified. And from a verification perspective, it's about 200,000 lines of Isabelle proof for that 7,500 lines of C code. And this took many years to develop with a lot of people. But the proof consists mostly of just a refinement statement, which says that any behavior you can observe of the C program is also observable in an abstract correctness spec. And this spec is much smaller than the program, so the hope is that you can state all of the correctness conditions that you want on top of that spec, all of the security properties or other things that you care about. So since then, they've done a lot of further verification on SEL4. Oh, this is not working. Okay. Since then, they've done a lot of verification on top of these abstract specs for security proofs and stuff like that. Integrity and non-interference and a number of other security properties. Also, they've done a worst-case execution time analysis, and they've extended the verification down to the binary level using SMT solvers to automatically prove refinement between them. So this is very impressive, but really, a microkernel is just a tiny part of the overall system that we'd want to depend on. So our systems people were very enthusiastic about this idea, and they wanted to start with more systems components, like file systems. After all, even the smallest embedded system usually depends on a file system, or 2, or 3, or 4, or 5, or 6, or maybe 10. So this is a bit of a problem for our formal methods engineers. And when we looked at the size of your average file system implementation, well, it's about the same size as SEL4 was. So if we're going to have to verify 10 file systems, that's just completely impractical using the existing verification techniques. So this is a big problem. A suggestion comes from a third party. Maybe we don't write the file systems in C. If we could write them in a better language, oh sorry, not a better language, a language that's more suitable for verification, then maybe we could reduce this cost. And who would make this suggestion but the programming languages people? I see Phil is here, So we wrote a paper on this about 3 years ago called File Systems Reserve Verification 2, advocating this language-based approach to simplifying verification. So from a formal methods perspective, our formal methods guy is very happy about this idea, very eager to get away from C. So if we're getting away from C, well, we want a language that integrates straight with a theorem prover. They want a language that has really easy to reason about semantics. No, none of this unsafe, undefined stuff. While we're wishing, let's say that we'll say every obligation that we want to prove about our program, we can just discharge by equational rewriting. I mean, this is a slightly impractical, but it would be nice if this were true. So we have this simplifier tactic in Isabelle, which just does a bunch of rewrites on your equation. We want to depend on as little code that is unverified as possible. So we don't want to have to trust anything more than we absolutely have to. And we want to avoid unpleasant reasoning about stateful computations. So for example, if you update a little bit of your state, you don't want to then have to reprove that the rest of the state didn't change when you made that one little update. This happens a lot, and it's very frustrating, very annoying. So from a programming language's perspective, we can say, well, we're going to need to formalize semantics if we're going to integrate it with a theorem prover. We're going to need memory and type safety for an easy to reason about semantics. We need equational reasoning if we want to use an equational rewriting tactic. And we'd want to maybe have no runtime system. Preferably, we don't want to depend on an untrusted or untrustworthy garbage collector or a runtime system with other fancy features. So we'll just cut that out completely. And we'll say, probably we'll need some sort of static aliasing control or something like that to manage this sort of stateful reasoning. Okay. Now, from a systems perspective, they're not really happy about moving away from C. They like C. C is a very popular language in the systems community. And so if we're going to use another language, it's still got to interoperate with C. So we're going to have interoperability with existing systems code. We need good performance, preferably as good performance as C. We need predictable runtimes, preferably as predictable as C. And we need similar allocation patterns to handwritten C. Okay. Well, so from a programming languages perspective, once again, we're going to need a C foreign function interface. We're going to need as close to zero cost abstractions as we can get. We need no runtime system. Fortunately, there's one thing that the formal methods and systems people can agree on. And then we have some mechanism to encode destructive updates, so we avoid allocating new objects every time we make a change to a data structure. So Cogent is a language that I designed and we implemented together. And it satisfies most of these goals. So it's a total, memory-safe, purely functional language. It generates pure, simple, shallow embeddings in higher-order logic, specifically in Isabelle. And these are just pure functions, easy to reason about equationally. And then it also generates some C code, which performs destructive updates. It behaves much like C code that you would write by hand. And it generates a proof that connects the semantics of the C code that it generates with the shallow embeddings that it generates. So this means that you can prove things about your shallow embedding and have it hold for the C implementation. It includes a C foreign function interface. You just need to provide suitable abstractions of your C functions for use in the higher level embeddings. And parametric polymorphism because it's 2016. And we have no runtime system, so everyone's happy. So you can see that here, I mean, I don't expect you to read this code, but you can see here that it looks like a functional language. Okay, so how do we do this? How do we manage to have a program with simple shallow embeddings and destructive updates? Well, we use uniqueness types. So Phil Wadler actually was one of the first people, I think, who noticed this fact. But if you have uniqueness types, which is simply say that you can only use a variable once, if it has a unique type, if you have that, then you can actually compile what looks like a purely functional update here, where I'm creating a new record with an updated field count, to an imperative program that actually destructively updates that object. Because X has already been used in this example, I cannot observe the change to the original X anymore. Whereas if I had returned the original x as well as the changed x, then if I had destructively updated it, then I would not be able to compile. If I had destructively updated it, then I would have been able to observe the change in both of the variables rather than in just one. So I would have lost the equational theory. But fortunately for us, uniqueness types rule this out. Plus, they also give us static control over resources, which means we can get rid of the runtime system. So from a verification perspective, the language has two semantics. The first is what we call the value semantics, and it's just a standard big step evaluation relation that takes expressions and gives you values, and it has an environment. And this is great for reasoning about. So it's good for connecting it to a manually written top-level specification. And we also have an update semantics, which is similar, but it's got a bit more machinery here to deal with destructive updates. So we have a mutable heap, and values can now contain pointers into this mutable heap. And so this is suitable for automatically generated refinement proofs down to the C code. So we have these two semantics, and we prove once and for all that for any well-typed program, if you follow all the pointers in the update semantics values, and you get these value semantics environment, and the update semantics evaluates, then the value semantics will evaluate, and the results will relate similarly. Okay? So this is a refinement proof, more or less. So just looking at this bottom part of our refinement chain, we have a number of representations that are generated per program. So we have the deep embedding of the update semantics where we connect it to that equivalence proof or the refinement proof. And we have the C code, and we import the C code into a simple language called simple. It stands for simple imperative language. And this is what we use for the semantics of C in SEL4 as well. We have a tool for abstracting away from some of the bits and bytes of C and giving us some more typed, shallowly embedded representation in Isabelle called autochorus, and this was published in PLDI. And so we use that just to give us some type abstraction. And then we wrote a paper at ITP this year, and Christine is here, I think, somewhere, and she was the primary author of this paper, where we defined a refinement framework that automatically generates a refinement statement connecting the autochorus output to the cogent program. So that's how we handled the automatic compilation down to C. But what about the connection between the deeply embedded language and the shallowly embedded, nice, easy to reason about, purely functional programs embedded in Isabelle? So here, we start with the value semantics. So we've already made the switch from the update to the value semantics. And then going up, we have a proof that relies on a very simple well-typeness theorem that says that the polymorphic program and the monomorphized version of that polymorphic program have the same semantics. After all, if you instantiate type variables, you shouldn't affect the semantics of the program. So this is a fairly easy proof to discharge. We also prove that a shallow embedding corresponds to the deep embedding. This is just a very simple refinement proof that we push through in a syntax-directed way. And then, now that we're on the shallowly embedded level, we can use equational reasoning to establish correspondence between the anormal shallow embedded, which looks like the internal compiler representation, and a neat shallow embedding that's very friendly, easy to reason about. It looks exactly like the code that you wrote as input to your compiler. And this proof that connects the neat and the anormal embeddings is just done by SIMP. It's just done by equational reasoning because we've already got that in our language. So this sounds great, right? But what's the catch? Well, if you take the space of all the programs you could write in C, and then you take the subset of that you can import into simple, which is a substantially smaller set than the original set of C programs. And then you take the subset of those that you can successfully abstract with autochorus. And then you take the subset of those that have no undefined behavior. And then you take the subset of those that are total, that always return a value. And then you take the subset of those that can be encoded using the fairly restrictive linear types that we use. Then you get the space of cogent programs. So this seems very restrictive. However, it doesn't matter so long as we can write most of our file system in that cogent box, or circle rather. So we did this. Sydney and several other of our systems people implemented a file system or two in Cogent. And they found that for the vast majority of file systems code, it fits in the Cogent bubble. There's just a little bit that doesn't. So this little bit that doesn't is actually things that we don't support in Cogent, like loop iterators. We don't have any built-in support for iteration, so you have to import higher order functions from outside. Data structures like B trees, allocators, and other things like this. So the good thing about all of this external code is that it could be reused between file systems. And indeed, the two file systems that we implemented, ext2 and a flash file system, do reuse these data structures. So we have a shared library between the two. So this means that we could verify that library once and amortize the cost of its verification over every single file system that we implement. All right. So from a performance perspective, we're not doing too bad. So we implemented the same file system in C and in Cogent. And for the most part, we have comparable performance. However, there are some pathological cases. So we sometimes sacrifice performance for verifiability. So for example, when you're searching through an on-disk data structure, right now in Cogent, the way to do that safely is to deserialize the entire data structure as you go, allocating it in memory until you finally find the thing you want, and then you throw away all the rest. This is very slow, and so you can see that we've got a substantial slowdown here for tar. But we have some ideas on how to improve this. See, the main issue with that particular problem is that if you search through the on-disk data structure, then you're going to need a pointer to the disk at the point you're searching and a pointer to the beginning of the disk buffer so that you can keep hold of it. So you end up with two pointers to the same data structure, which violates the uniqueness condition of the type system. So we think that adding region types to this language may solve this problem, although we haven't worked out all the details yet. So adding extra type system features might help improve this situation. Also, we're considering writing some extra DSLs for specific file system tasks like data serialization and deserialization that we can maybe use to plug those gaps. Also, just the slight overheads you see here, like the 30 to 31 seconds and stuff like that, that can be explained, I think, by the fact that we generate code that looks a lot like single static assignment form, but the C compiler that we use seems to ignore that fact and give us very large stack frames. So this is a solvable problem. It just requires a bit more engineering effort. Another thing that we can do to improve performance is perhaps on the top level, we could be using equational reasoning to do things like loop fusion or other high-level optimizations. This might be an interesting avenue for further research. From a verification perspective, our proof engineers are very happy. The purely functional shallow embeddings are a lot easier to reason about than C. I think I don't need to convince you of that. Type system can be used also to provide free theorems. So for example, we can say that the disk, if a function doesn't write to the disk, then you give it a read-only type. And then you know automatically that it's never written to by that function. So we can establish very complex state invariants just by encoding it the correct way in the types. So the total size of the language development in Isabelle is 16,423 lines of code and proof. And this includes the language formalization and the once and for all equivalence proof between the two semantics. We also have about 120,000 lines of proof generated for the file systems. So still to come in terms of verification, we want to be verifying those extra bits that don't fit into the Cogent bubble. And we also want to look at implementing and verifying further file systems. Also, from a language perspective, we have a few features. I already mentioned region types. We also want to look at a way to maybe encode the specification that you wanted to approve into the language itself. So we're not sure how that's going to look yet, but we're thinking of things like dependent or refinement types, or maybe something like quick check. All of these things are still up in the air. And I also mentioned a data description language and other specific file system related DSLs that we can use to improve file system verification specifically. And as Kathleen mentioned before, the elephant in the room, concurrency. We do need to support concurrency eventually if we want to support a lot of real-world systems. So concurrency is definitely on our to-do list, but rather far down. I mean, we need a concurrent semantics for C before we start with the concurrent semantics for Cogent. But definitely it's something we want to support. All right, thank you. That's it for my talk.
Questions? John, please stand up and introduce yourself.
Hi, I'm John Launchbury from DARPA.
Hi.
So do you know, this is really cool. Have you looked at, with SEL4, re-implementing any of that in Cogent? And have you done thoughts about that as to what the performance hit might be and how it might change the proofs?
Right, so SEL4 does a lot of things that we don't support. So I imagine if we tried to look at SEL4 in Cogent, then a lot of that code would end up not in the bubble of the space of Cogent programs. In particular, my feeling about this is because SEL4 has a lot of cross-cutting stuff where you have you don't really have a lot of modularity or anything like that. So and a lot of data structures that have funny pointers and things like this that we don't look at. So our type system offers a lot of simplification specifically for the use case of file systems, but it relies heavily on these abstract C parts. And I'm pretty sure in SEL4 most of the kernel would end up in those C parts rather than in the Cogent parts. But I haven't actually looked at it. It would be interesting to try, but I don't know how far you'd get here.
Derek?
Hi, I'm Derek Dreyer, Max Planck Institute. Can you go back to the slide with the concentric circles?
Yep.
Yeah, that one, right?
Yep.
Actually, and there was one more
Oh.
overlay. Or yeah, that
yep.
part. Right. So so this reminded me a lot of Rust. So I was wondering, because Rust has a similar approach of this core type system that's a substructural type system, and then there's the standard library extends the power of this type system by with
unsafe bits.
With unsafe features, right? And in Rust, there's a really challenging problem of just proving that the whole thing is sound, because the way that these libraries, the interfaces of these libraries are sort of, well, these libraries are really changing the meaning of types. I guess I would put it that way. So types that may appear to be unique types or linear types in the core type system, they may actually be shared. They may, an inhabitant of that type might be shared when it's implemented in a library. And so I'm wondering, do these libraries that you're verifying manually, are they, what kind of interfaces are they given? Like, are they given?
So do you mean like with respect to the proof, or?
Yeah, I mean, well, you use these libraries inside you refer to them inside the Cogent code, right? So I presume they have interfaces that have like uniqueness types. Do they change the meaning of types in the way that the Rust libraries do?
If you do, then you'll fail to prove. So if you import C functions into the Cogent program, then you have to prove certain things about those C functions, namely that they respect the invariants of the type system.
Okay, so you fix some invariants of the type system that are...
Yes, and the details of those invariants are in the paper.
Okay.
Yep.
Next question. Bill?
Phil Wadler, University of Edinburgh. That was incredibly nice work.
Thank you.
So I gather from what you're saying that you have no runtime system, so you get rid of all shareable pointers at runtime? Right, you say you've got a linear system so you can update things in place.
Yes.
And then presumably you're not using any garbage collection, or did I misunderstand?
No, we're not using any garbage collection.
So what I'm wondering about is lots of stuff can be made linear pretty easily. But it sounds like you're making everything linear, which I'm a bit surprised by.
No. We have a mixed type system that supports shareable things and linear things. And you can do the sort of borrowing thing where you make something read-only but shareable. And so I didn't mention these features because of lack of time, but yes, we do have features that support that sort of thing, and it does make our proofs a bit hairier, but it all works out in the end. The main thing is that we, unlike some other linear type systems, we don't allow you to explicitly share mutable things. So there's never any mutable shareable thing. So therefore you keep the equational semantics that we want.
Okay, and it turns out we've talked a bit about it is a restriction to write in that, but there's quite a lot you can do even within that subset.
Yes.
Very nice.
Yes.
And could I get a copy of your Lambda Man image, please?
Send it to you.
We are now out of time, so let's thank the speaker again.
Thank you.
So that's the end of this.